All right, so we are in chapter 2. And we're going to begin to look at word problems with trig. So how does this translate? It says we want to look at solutions and applications of right triangles. And so they discuss the idea of significant digits in this section, because when you start doing real world problems, then you want to think about what kind of accuracy you're using, where you should round off your numbers, things like that. Solving triangles, which we will look at the idea of if you don't know certain parts of a triangle, how you can use the parts you do know to figure out the parts you don't know. Angles of elevation and depression, meaning when you form an angle by looking up off of a level surface or by looking down below a level surface. Angles of elevation or depression, because these things go into real world problems that we'll also be trying to do examples of in this section. Okay, so moving forward. They initially talk about this idea of significant digits. I think this slide is a little bit off here. So I think there's supposed to be a divisor here, maybe about here. Something like that. So a significant digit is a digit obtained by an actual measurement. And the significant digits in the following numbers are identified in color. So let's look at these numbers and just try to get an idea of what they're talking about here. So if we look at this first number, 408, then they're saying all of those numbers were obtained by an actual measurement. So the fact that they wrote 408 and they didn't write 409 or 407 suggests that the 8 was a measured amount, that was actually determined, and that they might not have known what was in the decimal after that, the 10th place, the 100th place, but down to the whole number, they're accurate. If we look at this next digit beside that, they've highlighted all of the digits. And the idea is that you have 21.5. So this is 3 significant digits. You can sort of count up. There was 3 here. There was 3 here. And so the idea is that all of those digits were measured, that they knew it wasn't as high as 21.6, or they would have put that, or 21.4. But after the 5 to the right of that in the 100th place, we don't really know, and they didn't put anything there. So you could say it was rounded off to this position, but as the number is shown there are 3 significant digits of measurement. Now let's compare those to the one all the way on the right over here. So we end up running into possibly a little bit of confusion when there are zeros involved. So for example, on the very first one we did, 408, there's a 0 right in the middle of the number. But with this number all the way on the right, 7,300, there are zeros on the right of the number, and those are not identified with the blue color. So in this number, they're saying there's only 2 significant digits because they've only highlighted the 7 and the 3, even though the number itself is 4 digits long. So the idea behind this is a recognition that when numbers are taken through some sort of a measurement, that it is often the case that there's only so accurately you can measure something. And that after that, you don't know the smaller details that were beyond your ability to measure or were not being kept track of. So if I write this number 7,300, the reason we say this has only 2 significant digits is because when you have something that happens to land on the nearest 100 value, it usually would seem to appear that that's because you didn't count the individual values when you were taking the measurement. So for example, if I look at a very large group of people, It might be normal that I would say, I'm doing some estimations and it appears to be 7,300 people about were here. And so that I could only count to the nearest 100 in terms of accuracy because of the challenge of people moving around, and it's hard to count big groups or something like that. So when we have a number, we're basically going to use how many digits there were that in order for them to be there, those had to have been measured. So for example, with the first digit 408, because we know we measured beyond the tens place down to the ones place, we know the tens place was accurately measured, and that's why there's a 0 there. So all 3 of those places are significant digits. But with the 7,300, we know it was measured to the thousandths, to the hundredths, but after that, we don't know if that was just rounded off or had to be approximated. So significant digits is kind of a subtle concept. I don't think it'll be a huge impact on what we're doing here. But nonetheless, they bring it up here. It's worth discussing a little bit. And we can best grow to understand this, I think, through seeing examples done. And the way it's going to present itself is, as it says here on the bottom, your answer to a problem is no more accurate than the least accurate number in your calculation in terms of how many significant digits that you had. So let's say, for example, to try to illustrate this significant digits, I'm going to go have some blank space to play with. Let's say I want to determine the money needed to take a group to an amusement park. And so let's say we know that the ticket price is $4.25 per person. Then let's say we're going to say, well, how many people are we going to take? And then we'll figure out how much money we think we'll need. And so then let's say that a person says, we don't know exactly how many we're going to take, but round it off to the nearest 10 people, or we're going to have about 20 people. All right, so you have a calculation for the ticket price where you know that all the way down to the nearest cent, $4.25. So we would say, just using the language that we just discussed, that this number has 3 significant digits. Then when we say about 20 people, this only has 1 significant digit. Because the ones place, when we say about 20 people, is not measured accurately. I don't know if there's going to be 22 people, 21 people, but I'm thinking it's closer to 20 than it is to 10 or to 30. It's kind of been rounded off to the tens place because it's an approximation. So if we put those things together and then we try to talk about how much money is needed, well, if you have the price per person and you have 20 people and you put those things together, you would multiply how many people times the price. If I multiply 20 people times a price of $4.25 per person, then I'm going to get $85. Now, that's $85 even. and the price of each ticket was down to the nearest penny. So we can ask ourselves, well, what should be the answer to the question about how much money we would need, and how accurate can that answer be? So if I say $85 and no cents, 85.00, because tickets were known down to the nearest penny. Well, the problem with that is that we're claiming that we know exactly what we're going to have to pay down to the nearest penny, and we don't even know how many people are going to be there. The 20 was just the closest we could guess to the right answer. So it's silly to suggest that our accuracy would be down to the nearest penny, when in actuality, we don't even know how many tickets we have to buy. So this doesn't make any sense. So you could say, all right, well, let's say we just go down to the nearest dollar. Or how do we decide how far we need to go? That's what significant digits tries to help us with. Basically, the price of the ticket was a much more accurate measurement to help us with the cost than the number of people, because there was 3 significance digits of measurement with the price and only 1 significant digit with the people. So what they're saying when they say that your answer is no more accurate than the least accurate number in your calculation, that means when you write your answer, you should take the $85 and use only 1 significant digit, because then its accuracy in your answer matches the least accuracy in the numbers that you use to get that answer. So since I only had 1 significant digit in my number of people approximation, I want to round off my answer to the very first significant digit. So if I take $85 and just round it off to the first digit, 1 digit, then this would give me approximately $90. And so the idea with significant digits is if multiple numbers in a problem are used to get a final answer, then you should look at the numbers that were used and see how many significant digits they had, and whichever had the least, that's how many you can claim in your answer. If you only have 1 significant digit because one of your answers was really just a ballpark, well, then you should only have 1 in your final answer after you've done your calculations. So this has 1 significant digit to match the $20 number. Questions, comments, discussions about this at all?
Yeah, I have a question. So if you knew that it wasn't about 20 people, like if it just was 20 people, would that 0 become a significant number too?
Yeah, and sometimes you would need to somehow gather that information separately. Okay. Like if they said, we know there's exactly 20 people, well, then you can use whatever significant digits are claimed. Does that make sense? Yeah, so it's an attempt to have a mathematical process to deal with the vagaries of how measured quantities are communicated. And so if the vagary of a number being given without a specification, like 7,300, did you get exactly that? If that's not specified, you assume that they didn't, that's just as close as they could get. But if they said, we got exactly 7,300, then with that extra information, you know those extra zeros were actual measured values, and then you can include them as significant digits, if that makes sense. Other questions, comments, discussions about this idea?
Why it is the 90, not the, it cannot be a 80?
Well, typically we would round, and the rules for rounding up is that if the last digit that you're rounding up is a 5, then you would round up the digit preceding it. So if you're rounding up to the very first digit and the second digit is a 5, then you round up the first digit. If it was 84, then we would say about 80.
Okay.
Does that make sense?
Yeah, okay.
Yeah, thanks for the question. Yeah, so rounding, and maybe I'll put that here, round to 1. Round to first digit. Yeah, thank you, thank you.
I have a question.
Yeah, go ahead.
So why are we rounding to one significant digit? I know it's because 20 is one significant digit, but why don't we do the 3 significant digits? Like, what makes us choose the 20?
Yeah, thanks for the question. So the idea is when you give your final answer, you don't want to give an answer that suggests more accuracy than you actually know. So for example, if I'm saying, well, I have 3 digits for the person, and so when I multiply these together, I'm going to get $85 down to the nearest dollar. But I don't know that it's actually $85 instead of $86 or $84. Why do I not know that? Because when I had 20 people, it could be 21 or 22. The inaccuracy of the 20 people forces that level of inaccuracy in your answer. So if I had 21 people instead of 20, then I'd have to add another $4.25. And that would actually put it up close to $90. So we don't want to claim a bunch of accuracy in our answer if there were problems used to get that answer in which that level of accuracy was not known. That's the explanation behind that. Does that make sense, Ella? Or or should I give a different example maybe if that's still confusing?
No, it makes sense. Thank you.
Yeah, if you used some approximations or there were certain things where you just didn't have a high level of accuracy, then you have to recognize how that's going to impact your answer and mean your answer also therefore doesn't have a high level of accuracy. And so you try to get your answer to match the lowest level of accuracy that was used because that's all you can really feel comfortable claiming. Anything more than that would be more than you really know. Great questions, great discussions. Okay, so having started off this section with this idea, we'll basically warm up to this as we put it to use as we're doing problems. And so the next thing we want to look at in this section here, and they just have some examples where they use angles and they show different ways like with degrees or with degrees in minutes or with a decimal version of degrees, how many digits of accuracy you can claim. So they have a little table to have you just think about that. So that will mean when we're doing things, we want to look at angles or side lengths or measurements of things and begin to consider how many digits of accuracy are in the numbers so that if we use them to do a calculation, we can have an appropriate level of accuracy in the final answer we give. But now we have our big first skill that we want to develop out of trigonometry. So far in our trigonometry, we've been learning these sine functions and cosine functions and talking about points on a unit circle or triangles and ratios of sides, SOHCAHTOA, TOA, all of these things without any real reason of why we would ever use any of this in the real world or how this would ever be helpful. So the key starting point for how trig immediately becomes applicable in the real world is solving triangles. So what does that mean? Solving triangles. To solve a triangle means to find the measures of all the angles and sides of a triangle. We know a triangle by the definition of a triangle has 3 sides and has 3 angles. So the first thing we're going to do to warm up to this process of solving for parts when we don't know some of the parts is we want to set up a convention or a standard way for labeling our triangles, the sides and the angles. So you're going to have triangle A, B, C, where you can kind of see these points in the corners. And you could imagine the points going from A to B, from B to C, from C back to A forms the triangle. but we're also going to use these capital letters typically to represent the measurement of the angle in that corner. So we have angle A, but made it into a nice straight line for me. That's nice. Angle B, not that time, and so on. So when we have an A here, we're thinking that that's this angle measurement is capital A here. And then in a triangle, if you go to the side opposite that angle, directly straight across from it, we're going to use the smaller version of that letter, little letter A, to represent the length of that side. So the length of the side opposite angle A is using the little a. And the same for the others. So opposite angle C is little side C length, and opposite angle B is little side B length. This is just so that we can quickly refer to the different parts of a triangle we're working with and know which ones we're talking about. So they immediately do a problem with kind of funky angles. So let me instead go back up and use and have us go over a simple example. In fact, I think I'm going to get a fresh page for us. Let's do this. Let's go back and get some fresh scratch paper to use here for this further exploration of this discussion. So I'm going to make a triangle here. This is going to be a right triangle. I'm going to call this A. So that's where angle A is. So that means little a would go over there. And that means I'm going to go this B up here. And that means the bottom would be little side B length. And then in this case, C is a right angle. So we kind of know that's a right angle, but that means the opposite side over here is going to be angle C. So the idea of solving a triangle is that we know some of this information. There's 3 angles and 3 sides. We know some of the sides or some of the angles or something like that. And we want to solve for all of it. We want to know all 3 sides and all 3 angles. We want to find the missing parts when we don't know something. So the first example I'm going to point out to you is that it's possible, because we looked at something called similar triangles before, it's possible that you could have a triangle that has certain side lengths in it. So let's say this was 40, this was 50, and this was 90. And then I could have a totally different sized triangle that had the exact same angles, 40, 50, and 90. We called those before similar triangles. Well, what this means is that if I know the angles of a triangle, there's no way that I can necessarily know the sides. Because it's quite possible you could have 2 different triangles that have the exact same angles, but the sides are all different. Like maybe the bigger one, all the sides are twice as big as the smaller one. So if I'm trying to imagine how I can solve for sides of a triangle, the first thing is that if I'm going to find out what all 3 sides of a triangle are, I'm going to have to know at least one of the sides of the triangle. If I don't know any of the sides, I can never figure out the sides, because with those same 3 angles, I could have all kinds of different side lengths. So let's give a triangle as an example and talk about how we might try to solve for it. Let's look at an example to solve a triangle. So let's say I have a triangle. And again, this isn't drawn to scale, just drawn quick and crappy. And let's say I knew that the height, the distance on this side on the right here was 10 feet. And I know that this is a right triangle, so I know this angle down here. I know angle C there. And let's say that I knew that this angle down here in the corner was 30 degrees. So what do I know about this triangle? What do I know? I know two angles. There's a 30-degree angle that I marked there, and there's a 90-degree angle because it's a right triangle, and that's marked. And I know one side. It's the 10-foot side. So that means there's one angle that I still don't know up here. And then there are these two other sides. I'll use the letters from the example above. I'll call this little c here, and I'll call this little b here, and this would be angle B that I don't know as well. So those are the three things that I don't know. I know two of the three angles, and I know one of the three sides. So in this problem, we can find out from the three things we do know, all three of the things that we don't know. So let's start with the simplest beginning. If you ever know two angles in a triangle, then you can figure out the third one because they add up to 180 degrees. We did examples of this already early on. So in this case, for example, I know that, go up here. I know that B, angle B, plus 30 degrees, plus, and I could add the 90 and say they add up to 180, but we also know in a right triangle that the two acute angles, when there's two acute angles like this, add up to the other 90. So I know that B plus 30 degrees equals 90 degrees. And if I solve that for B by subtracting 30 from both sides, that tells me that angle B has to be 60 degrees. So I'm going to fill that in here. So I now know the 60-degree angle. So maybe we can recognize that this was one of our popular triangles. We want to remember a 30, 60, 90-degree triangle. But even if it wasn't, we still could have found out that missing angle. So now the only thing we need to figure out are sides B and side C. So here we did angle B. So now let's do side C. So we want to know what that hypotenuse of this right triangle is. Well, if we knew both of the other sides of the right triangle, then we could use the Pythagorean theorem to find out the missing side. But we don't. We just know one of them. I don't know B, and I also don't know C. So what we want to do now is use a trig function. And what we want to look at is the side that we know and the side that we want. So I'm going to say, again, let me put in the rest of some of these labels here. Whoops. So for example, from above, this is angle A, and this is side A, and this is angle C. All right, so we want C, and we know side A and angle A. So we can relate these three things together, side A, angle A, and side C, using a trig function, by taking note that side A is the opposite side to angle A, and side C is the hypotenuse of the triangle. And we know what relates the opposite and the hypotenuse of an angle? The sine. So from this, we relate to the fact that sine of angle A is equal to the opposite, which is side A, divided by the hypotenuse, which is side C. And the reason this helps us is because this we know And sine of an angle, where we know the angle, we also know, because we can just punch that into a calculator or remember what sine of 30 degrees is. So when you have an equation where three things are related to each other and you know two of those three things, you can solve for the one that you don't know. And that way we can solve for side C in this triangle. So how is this going to look? When I'm looking at the triangle, I want to get side C. I see that I have opposite A is a 10 and angle A is 30 degrees. So then what I write then is that sine of 30 degrees, which is opposite over hypotenuse, is going to be equal to the opposite side of length 10 feet divided by the hypotenuse, which is what I don't know, which is C. And so then we solve this. Solve for C. So let me pause there and see if there are questions about how I set up this little equation to solve before I actually carry it out. So we're using the SOHCAHTOA, the idea that the sine in an acute triangle can be found for an angle A by doing the opposite divided by the hypotenuse. Cosine would be adjacent divided by hypotenuse. I actually could also solve for C by using the cosine of the 60-degree angle, because then the 10 would be the adjacent to that and C would be the hypotenuse. So let's say I point that too, or I can say, I can point that out as well. Or I can say, or along the same lines, we could solve for C by recognizing that the 60-degree angle, which is also known in this triangle, can be used. But if I'm doing the 60-degree angle, then the side that I know, the 10-foot side, is now the adjacent side to that angle. So this is adjacent to 60 degrees, but it's opposite to the 30 degrees. And we want to use the 10 because that's the one we don't know what the B is. So if I'm using the 60-degree angle and that's 10 is adjacent to that, then I would do adjacent over hypotenuse, which is cosine. So that would be that cosine of 60 degrees is equal to the adjacent side to 60 degrees, which is the 10 feet, divided by C. And I would solve that for C. And you may recall when we were looking at these acute angles and triangles that sine of 30 degrees is going to be the same as cosine of 60 degrees. And that's why we could use either one of these, because those two things on the left come out the same. That's because these are the same. Questions, comments, discussions about any of that? All right, so then let's continue with the solving process. So if I take this equation that I want to solve, how do I solve that? Well, I've got a fraction on the right side. And when you have a fraction in an equation, typically the way you begin is by getting rid of any fractions. And you do that by multiplying both sides of the equation by the denominator or the lowest common denominator. So I would multiply both sides by C here, because then these would cancel out. Yeah, question?
What are we solving for? Are we breaking apart the triangle and trying to figure out how to find sides and stuff? Or
Why are we trying to solve for the parts of the triangle we don't know? Is that what you're asking?
yeah, is that what we are doing?
Yes. So I said we want to solve a triangle. And solve a triangle, as we just defined on the slides, is when you find all the sides and all the angles.
Okay.
And so in this example, I said what we know is 2 angles and 1 side, and I want to show you how we can figure out all the stuff we don't know, the other 2 sides and the other angle.
Okay.
Does that
Thanks.
make more sense now?
Yes, very much.
Okay, great. So yeah, so I started by getting the 3rd angle and figuring out what that was, and now we have to find B and C. And so the process I'm using here is to figure out what C is. So solving this little equation, I multiply both sides by the C variable, and then this becomes that C times the sine of 30 degrees is equal to 10 feet. So then to solve for C, I would divide by sine of 30. Whoops, sine 30. And those would cancel, and I'm left with C is equal to 10 divided by the sine of 30 degrees. Now at this point, you can type that in your calculator. We may remember from a 30, 60, 90 degree triangle that the sine of 30 degrees is 1/2. You could also look that up on the little chart that we made last time of some common angles. Somehow you have to come up with what sine of a known angle is. And in this case, that's one you may remember. So that would mean that C is equal to 10 divided by 1/2, which is 20. So I was able to solve for C in this triangle, and I go back up here, and now I know that C is equal to 20. And this would be feet because it's the measure of the side length. Now that also might make sense because in a 30, 60, 90 degree triangle, we may remember that the shortest side is half the hypotenuse. And in our case, the shortest side was 10. And so therefore the hypotenuse would have to be 20. But we didn't have to remember that or know that. You can solve using this little formula. And if it wasn't this nice triangle, if it was 29 degrees or 25 degrees, whatever it was, we can solve using this process. So I get that all on one page so we can think of it together. Questions about how I solved for C? That's definitely the hardest part of this problem. Well, now we have a right triangle where we know 2 of the sides. Side A is 10 feet, side C is 20 feet. So if it's a right triangle, then we can get side B by using the Pythagorean theorem, because A squared plus B squared equals C squared. So let's say I just did that. Now we could also use another trig formula, like I could use cosine of 30 is the B side divided by 20 or something like that. But let's just go back to the Pythagorean theorem. So A squared plus B squared equals C squared in the Pythagorean theorem. And now I know A is 10. I don't know B, but I know C is 20. So 10 squared plus B squared is 20 squared. That's 100 plus B squared is 400. Subtracting 100 from both sides, I'd get B squared is 300. And then square rooting both sides, and I don't need to use a plus or minus because I'm talking about B is the length of a side, which would only be positive. That gives me that B is the square root of 300. So that's a number. You could type that on a calculator and get whatever level of accuracy you want, maybe looking at things like significant digits. But we could, for the moment, leave this as an exact value and maybe even simplify it because we can simplify a radical. So I'll just do that real quick and imagine the calculator work can be later. This could be factored into the square root of 100 times 3 because 300 is 100 times 3. And then I can take the square root of 100 to get 10 and leave the square root of 3 because that doesn't come out nice. So my final answer for B is 10 times the square root of 3. Which again, I could type on a calculator if I wanted a decimal or something like that. And that will be in feet. So I go over here to B, and now B is equal to 10 times the square root of 3. That would be feet, whatever that number is. And now we know A, we know B, we know C, we know angle A, angle B, angle C. So we have solved the triangle. And you can always do this. Questions?
Tricky question. Is sine trying to find the line of A to B and from B to C? Don't know if that's
You're asking about sine?
yes. So the sine.
Relates the opposite side over the hypotenuse side.
Okay. Okay. So if I'm correct, it's trying to find the distance, as in the length of those two lines, right?
Well, that was our goal for this problem, and we chose to use sine to do that. We could have also used cosine. As I pointed out down here, you could use sine or cosine.
Okay.
Like
Thank
here it was using sine, and this one would be using cosine. Either one would work
Okay.
because they're just a tool, and both of them would do the problem. They relate the sides together. All right. So we need to go through this process multiple times, but you want to get very comfortable at solving triangles because it's our #1 way to do real world problems, especially using trig like this. So let's do a real world problem where this process would be used, because then we can practice the process again, and then also we can see what it starts to look like in the real world. And so I've done this with like classes before that meet in person, where we actually go outside and do this physically. But let me just draw a picture, and I'm going to give you guys a problem and give you a couple of minutes to think about it and give it a try if you're willing. But even if not, after that, I'm going to do it for you. But here's a statement of the problem with a picture to go with it. All right, so let's say there's a tree here. And the tree is pretty much straight up and down off of the ground. And you're maybe laying in the grass over here, but basically your head is down here on the ground and you're looking up at this tree. And when you look up at the top of the tree from, we're going to call it basically a point on the ground where your little head is here, you're looking up with an angle that's 40 degrees. Actually, I'm going to just make a nice triangle. Let's say 30 degrees. So it's the same kind of triangle we were just looking at. So when you look up at the top of the tree, there's a 30-degree angle formed. That is called an angle of inclination, because it's how much you lift it up off of a flat surface in order to look up at something. That's called an angle of inclination. And you can actually make one of these like with just little household items very easily to measure an angle of inclination. But in any event, let's say we know that this angle that you're looking up is 30 degrees. And when you lay down here on the ground, you walked past the tree. And what you observed was that this distance here on the ground is measurable. In fact, here's a way you could have this be measured very easily. Let's say the sun is up here shining. And the angle up to the top of the tree is the angle from the place where the shadow on the ground is. So you've got a shadow on the ground of the tree here. And if you go to the very top, tip top of the shadow of the tree on the ground, and you have the angle up to the top of the tree, it's 30 degrees, maybe because you just lay down there or something. But the length of the shadow, we're going to say, is 60 feet. You could just measure that on the ground, maybe walk some paces or get out a tape measure or something like that. So when there's a tree that casts a 60-foot shadow, and the angle of inclination from the tip of the shadow to the top of the tree is 30 degrees, then we can ask the question, how tall is the tree? So because the tree is straight up and down, I'm going to just make sure everybody is clear that that means that this is a right angle of a triangle that's formed here. So the shadow on the ground is 60 feet. The angle up to the top of the tree from the top of the shadow is 30 degrees. And from that information, we want to know how tall is the tree. So I'm gonna stop everything for about 2 minutes. Okay, so does anybody want to ask a question if you kind of feel like you wanted to get started, but you really didn't know what to do? Or does anybody want to have a discussion about this problem before I sort of lay out an idea of how you would go about doing it? Comments, questions, discussion?
When I saw it, I saw the trig function 10. So since the values are mostly at the adjacent and the hypotenuse, so I think that would be a good starting point to trying to find the opposite. Yeah, opposite.
Okay, so tan, I think you said, is that right?
Yes.
So tan is not adjacent and hypotenuse. It's opposite over adjacent, right?
Okay, so then I will be wrong.
But no, you're right.
Basically-
Tan is the right thing to use. You just said hypotenuse, and we don't need the hypotenuse here. But I think tan is the right function. So I think you have the right idea.
So what I got was tan. Tan is like, since the degree is 30, so it would be tan 30 equals like x, since we don't know the tree. We don't know the opposite over 60. That's what I put, but I'm not.
That's perfect.
Okay.
But it makes sense. We're all a little concerned or not sure, but that's exactly right. So this is why people remember SOHCAHTOA, because it helps them when they're looking at the triangle to figure out what sides are involved. So if I want to know, and for people who just didn't know how to get started, let's talk this through a little bit. If I want to know how tall the tree is, that's our unknown. So we can put an X there or an H for height, or you can put whatever you want. So the two sides that are involved are the 60-foot shadow side and the X, the unknown height. Those are the two sides of the triangle. The angle that we know right out the gate is 30 degrees. The X side is opposite that angle, and the 60-foot is adjacent to that angle. So we have the opposite and we have the adjacent angles. And from SOHCAHTOA, we know that the tangent is the opposite over adjacent. So since the tangent is the trig function we use for opposite and for adjacent, we choose that function. And therefore, from that relationship, we know tan of the angle is the opposite divided by the adjacent. So tan of 30 degrees is the X divided by the 60. And so that's the perfect equation. And then we solve that and get our answer for how tall the tree is. But let's pause there and see if there's a question about how we set that up.
Mine is a different question. So if I put into the calculator tan 30, it gives me square root 3 over 3. Can you explain into what will constitute that? What will that value basically mean? I don't know how to think about
What does that value mean? Is that what you're asking?
Yes.
So the tan is the sine divided by the cosine. It's a ratio of sides. It's a fraction of sides. So that means anytime you have a triangle where there's a 30-degree right triangle like the one we have here, anytime you take the side opposite to the 30 and divide it by the base side there, the adjacent to the 30, you always get square root of 3 over 3 every time. That never changes.
Okay.
That's a constant ratio of those sides in any triangle like that or any triangle similar to it.
Okay.
Does that help?
Yes, a lot.
Now we could also do that calculation by remembering that tangent is sine over cosine. So you could do sine of 30 and divide by cosine of 30 to get that number, square root of 3 over 3. Or some calculator would give you that or a decimal. So if I do square root of 3 over 3 is equal to x over 60. And I'm trying to solve for x. So then I would multiply both sides by 60 to get x by itself, since it's divided by 60. And if I multiply by 60, I can cancel 3 goes into 60 20 times. So that I end up getting that x is equal to 20 times the square root of 3 feet. And of course, I could type that in a calculator and approximate to whatever significant digits I wanted. And I found out the height of the tree. Square root of 3 is something like 1.4, something like that. So this would probably be something around 28 feet. But approximately 28 feet. Or maybe if I just do one significant digit, since the 60 only has one significant digit and the 30 does, that would be about 30 feet. So if you look at this, it kind of starts to give you an idea of how powerful trigonometry is, especially in situations where triangles are involved. That basically, by measuring the angle up to the top of the tree and how big the tree's shadow is, you can calculate the height of any tree. And that's a hard thing to do without having to climb it or do something like that. If you want to calculate the height of a building, you can just look at the shadow and what angle you have to tilt your head up to look at the top of the building. So finding missing sides of triangles in the real world is a very powerful application of trigonometry. It allows you to find lengths or distances that you're not able to easily traverse yourself. You can find how far a path would be through a mountain if you're going to drill a tunnel through a mountain to make a tunnel. And you want to know how far do we have to go? Well, you can use trigonometry to calculate that by making a triangle that kind of goes around the mountain and a side that goes through it to measure that distance. So that's the kind of problems we're going to see in the exercises that the book gives us and that we get in our exercise sets.